In this video, we are moving from simply describing data toward making decisions about unknown populations. Up to this point in the course, we have mostly focused on summarizing what we observe in a single data set and on using probability models to describe randomness. But statistical inference requires us to think one level deeper. Instead of only asking what this particular sample looks like, we must ask a much more powerful question. How would our statistic behave if we repeated the sampling process over and over again? That question is the gateway to the idea of a sampling distribution, which is one of the most important concepts in all of statistics. In statistics, you will regularly encounter three different kinds of distributions. These are the data distribution, the probability distribution, and the sampling distribution. Although they are closely related, they answer very different questions and operate at different conceptual levels. Students often mix them up, so it is important to clearly separate them in your mind. As we move forward into inference, keeping these distinctions straight will help you understand why many statistical procedures work the way they do. Let's begin with the data distribution. The data distribution is simply the distribution of the raw observations in one sample. It is empirical, meaning it is based directly on the data you collected. Because it depends on the specific sample, it will change from sample to sample. We usually visualize the data distribution using tools like histograms, dot plots, or box plots. Conceptually, the data distribution answers a descriptive question. What does this particular sample look like? It does not tell us directly about the population, it only summarizes what we observed. For example, suppose you measure the blood pressures of 50 patients and create a histogram of those 50 values. That histogram is the data distribution. It reflects only those specific 50 people. If you collected a different random sample of 50 patients, the histogram would likely look somewhat different. This variability from sample to sample is exactly why we need statistical inference in the first place. Next is the probability distribution. Unlike the data distribution, the probability distribution is theoretical. It describes how individual values behave in the population over the long run. Probability distributions are defined mathematically. Examples include the normal, binomial, and uniform distributions. You can think of the probability distribution as representing the data-generating mechanism for individual observations. It answers the modeling question. How do individual observations vary in the population? Continuing our earlier example, we might assume that adult systolic blood pressure in the population follows approximately a normal distribution with mean mu and standard deviation sigma. That normal model would be the probability distribution. Notice the key difference. The probability distribution describes the behavior of individuals in the population, while the data distribution describes what happened in one particular sample. Now we arrive at the sampling distribution, which is the critical bridge to statistical inference. The sampling distribution is the distribution of a statistic, such as a sample mean or sample proportion, computed from all possible samples of a fixed size n. It is also theoretical. But unlike the probability distribution, it concerns statistics rather than individual observations. The sampling distribution answers the inferential question. How much would our statistic vary if we repeated the study many times? Why does this distinction matter so much? Because these three distributions live at different conceptual levels. The data distribution describes variability among individual observations in one sample. The probability distribution models how individual observations behave in the population. And the sampling distribution describes how a statistic varies across repeated samples. A helpful rule of thumb is this. Probability distributions describe individuals, while sampling distributions describe statistics. Keeping that rule in mind will prevent many common mistakes. Let's look at an example involving salamander lengths. Imagine an ecologist studying salamanders in a swamp. Suppose the true lengths in the population follow a right-skewed probability distribution, where most animals are small, but a few are unusually long. That underlying model is the probability distribution for salamander length. Now, suppose the ecologist goes into the field and randomly captures and measures 20 salamanders. She plots a histogram of those 20 measurements. That histogram is the data distribution. If she repeated the field work tomorrow, she would likely obtain a slightly different histogram because the sample would be different. Next, imagine a thought experiment. Suppose the ecologist repeats the same 20 salamander study hundreds or thousands of times, and each time she computes the sample mean length. If we plotted a histogram of all those sample means, that histogram would be the sampling distribution of the sample mean. Notice the shift in focus. The data distribution describes individual salamanders, while the sampling distribution describes the sample mean across repeated studies. To fully understand inference, we also need to clearly distinguish between parameters and statistics. Much of statistics revolves around using information from a sample to learn about a population we cannot fully observe. These two concepts, parameters and statistics, play very different roles in that process. A parameter is a numerical summary that describes an entire population. It is fixed, but usually unknown. Common examples include the population mean mu, the population proportion p, and the population standard deviation sigma. Because populations are often very large or even conceptual, we typically cannot measure every individual, so the true parameter value remains unknown. A statistic, in contrast, is a numerical summary computed from a sample. Statistics are observable because they come from data we actually collect. Common examples include the sample mean x bar and the sample standard deviation s. Unlike parameters, statistics vary from sample to sample because different random samples produce different values. The central goal of statistical inference is to use statistics to estimate parameters. We hope that a well-chosen statistic will be close to the corresponding population parameter. But because of sampling variability, it will not match exactly every time. This unavoidable randomness is precisely why we need the sampling distribution. The sampling distribution tells us how much the statistic typically varies, whether it tends to be close to the parameter, and how uncertain our estimate is. If the sampling distribution is narrow, our statistic tends to be close to the parameter and the estimate is precise. If the sampling distribution is wide, there is more sampling variability and less precision. Let's work through a small population example. Suppose we have a population of 20 adults and we want to estimate the proportion who are left-eye dominant. If we look at the full population, we can compute the true proportion directly. In this example, the population proportion P equals 9 out of 20, or 0.45. But in real life, we usually do not know the population value. Instead, suppose we take one random sample of size 5 from this population. From that sample, we compute the sample proportion, p hat. In the example shown, the sample estimate is 0.4. But remember, this is only one possible sample. A different random sample would likely produce a different estimate. In fact, there are many possible samples of size 5. The total number is given by the combination formula, 20 choose 5, which equals 15,504 possible samples. Each one would produce its own value of p hat. This highlights why a single sample never tells the whole story. If we computed p hat for every possible sample and plotted the results, we would obtain the sampling distribution of p hat. That distribution shows the pattern of variability in our estimator across repeated sampling. This is the key object that allows statisticians to quantify uncertainty. In real applications, populations are often enormous, and the number of possible samples become astronomically large. For example, from a population of 1,000 individuals, the number of samples of size 5 exceeds 8 trillion. Clearly, enumerating all possible samples is impossible in practice. Fortunately, probability theory provides powerful results that allow us to understand sampling distributions without listing every possible sample. These theoretical results form the foundation for confidence intervals, hypothesis testing, and much of modern statistical inference. As we move forwards, the concept of the sampling distribution will become one of the most important tools in your statistical toolkit.